Let me start by introducing myself. My name is Gordon Cooper. I'm the product marketing manager at NXP for our high-end microcontrollers and the LPC4300 and the LPC4300. So we'll talk about both today, but primarily, and I'll jump ahead here, since I believe in truth in advertising, this is what we put on the abstract. So hopefully this is what attracted you here, and hopefully this is what I'll be covering today. So the interesting questions are, what is the difference between an M3 and an M4 from a benchmark point of view? Maybe I'm interested in MCUs. Maybe I have a DSP application. And how good at the M4 at doing DSP operations? So we'll talk about those as well. And then, okay, you've got a dual core, but is there really a benefit to that? And is it sounds complicated or it sounds exciting? It depends on your perspective. And so we'll talk about some of the trade-offs of what the dual core brings you and a little bit about the organization. To some extent, this is the first of 3 sessions. For the other 2 sessions today, there are more sessions on the peripherals and the dual core of the LPC4300. So the next session, 215, talks about our SPI flash interface that I'll mention briefly here, and about how the interprocessor communication works. And then the session after that at 3:30 maybe, is basically talking about 2 more peripherals, our state configurable timer and our serial GPIO. Okay. So from an ARM perspective, everybody here is an ARM licensee on the show floor or supporting the ARM cores. So what makes anyone different from the other? We used to be able to say, well, at NXP, we're going to have the fastest processors, the best flash speed. Well, competition has caught up a little bit, so now what else do we differentiate? Peripherals, how we do the core, how we do the support. So those are all things that we can talk about. We'll talk a little bit about the differences of the M cores. I won't spend a lot of time on it, but just to set the stage of what we're talking about. First of all, from an NXP point of view, where Philips Semiconductors spun off 6 or some years ago, and in the microcontroller division, we had a lot of 8-bit processors, 8051 type. We then went on to be very successful with the ARM7, our LPC2000 family, and ARM9, and we've completely focused moving forward now on Cortex-M in the near future, and that means the M0, the M3, and the M4. And we'll talk about what the differences of those 3 processors are. So if you're coming from an ARM7 background, and we see a lot of our customers at NXP have used the LPC2000 family, are still using it, but if you're making that transition, it's good to say, well, why did ARM redesign and go from the ARM7 to the M3? And as we look at the feature set up here, the differences, what you tend to see is that power consumption is better for the M3 core, performance is better, memory protection is added, more sleep modes, less latency. So basically, they took their very successful core, 32-bit core for microcontrollers, and optimized it and came out with the Cortex-M. So if you had to pick right now, unless you had some legacy reason to pick the ARM7, you should strongly consider the M3 core as a sort of comparable, solid, middle-of-the-road microcontroller. One catch, however, is along the way, they changed the instruction set. So if you're starting with an ARM7 design, moving to a Cortex-M, if everything is in C, it should be more or less a case of recompiling. But there are slight differences in the instruction set, going from the thumb instruction to the thumb 2 instruction set. The good news is once you've gotten to the Cortex-M family, all of the M's are based on that same instruction set. So the M0, the M3, and the M4 all are code compatible. Okay, so from an NXP point of view, right now we're the only company right now with M0, M3, and M4. Our competition is starting to see the attraction of the M0, and there have been some announcements on that. If the M3 is the replacement to the ARM7, well, what are the M0 and the M4? Well, the M0 is a realization that there's a whole host of 8 and 16-bit architectures out there, and why not go after those and say, hey, we'll give you a 32-bit core, so much friendlier with C compiler. But to do that, what do we have to do? We have to make it smaller. We have to make it less power. We have to make it more cost competitive. So we have actually on the M0 space, we were the first to come out with the Cortex-M0, the 1100 family, very small in terms of size, but big in terms of capability. So you can have up to 32K of flash. You've got the M0, different sets of peripherals. We've just announced a version with a USB device. That would be the 11U. We have an 11C, which adds CAN for you, and a version with a CAN transceiver. So it's on the low end with sort of one-off peripherals. So you can pick a part and drop it in. Now, from a pricing point of view, where we've announced some time ago that it was 65 cents. We had a press release on a new package to help drive our costs down even more. But we're still in the 50-cent range and above. So there are some 8 bits that really low end that might be unique. But anything else, you should really consider a 32-bit architecture, which makes your life much easier from a development point of view, much easier from a compiler point of view. Now, if you choose the M0, the M3, or the M4, you can use the same set of tools. So if you use Kyle or IAR, or we have our own version of the tools that you can download called LPC Expresso, it will work on all the processors, making your life a little bit simpler. All right, so M0, M3, what's the M4? Well, now there's the DSP space to go look into. So ARM said, let's take the M3 and add some DSP extensions. As it turns out, the M3 actually does DSP, and we'll see some benchmarks later. The question really is DSP is how fast can you go? What's the sampling bandwidth that you have to deal with? The difference between the M3 and the M4 we'll talk about in more detail, but effectively they've added single cycle multiply accumulate instructions that allows you to do math functions like an FIR, an FFT, or an IIR much faster. And we'll talk about all those in more detail. Actually, so the question is, was that floating or integer? They're all 32-bit fixed point processors, but ARM added an optional floating point unit. Optional meaning the licensee can decide whether to put it in or not. And all our M4s right now have that floating point unit. So it's a 32-bit fixed point processor with floating point unit attached. And I'll talk about that a bit more. But very good question. So from a pin compatibility point of view, the 1800 and the 4300 bridge that gap. You can actually design an 1800 and M3 in. It's pin compatible, part number compatible, and you say, well, now I want to add dual core, now I want to add DSP. You can drop into that same socket, the 4300. On the low end, the 1100 and the 1300 share compatibility to cross that boundary. And if you're starting from the LPC2000 and the ARM7, the 1700 has a lot of pin compatible versions to help you make that transition to the Cortex side. An ARM slide, but it shows you the instruction set of the different cores. So in the bottom left, you see the Cortex-M0. The M1 was more of an ASIC or FPGA. I'm actually not that familiar with the M1, but it wasn't a FPGA. So in terms of processors, the M0, the M3, and the M4. The M0 has a small instruction set. The M3 includes everything that the M0 has, plus additional instructions. The M4 has a lot more instructions. You can see in the pink there, almost all those instructions are the single cycle multiply accumulate, or some SIMD capabilities, single instruction, multiple data. Now that helps you if you're doing optimizations. It helps you if you're doing maybe some stereo things. C compilers don't handle SIMD very well. So that tends to be more if you're going to get your hands dirty with the assembly code. On the very top, as you asked about the floating point unit, those are the instructions that go with the floating point unit. So there's some specific instructions for the floating point unit. Key things here is every core can use the same set of tools, and code that you write on the M0 will run on the M3 and in the M4, and the M3 code will run on the M4. You're probably writing in C code. It probably doesn't matter anyway. You'll recompile it, but if you do try to optimize libraries, it's nice to know that the libraries are compatible.
Is there a lot of pipelining for instructions?
There's only 3 levels of pipelining in the M family, so it's not a tremendous amount of pipelining. Obviously, that's one way the DSPs go faster if they really stretch out the pipelining, and then, of course, when you have an interrupt, you got to flush all that out. So for now, I think it's 3 levels of pipelining, and in the M4, some predictive calculations. So from a benchmark point of view, how efficient is the core? So one way to look at it is dry stones, and dry stones are basically some programs that are run through the C compiler to determine the general processor performance. So these are ARM metrics for the generic core, regardless of NXP or our competition. This is what's advertised on the ARM website. So the Cortex-M0 has 0.9 DMIPS per megahertz. The Cortex-M3, so running the same code, it's level of efficiency, if you will, of the core. You can see the M3 and the M4 have the exact same efficiency. Well, why would that be if the M4 has a lot more instructions? Well, the truth is, M4 is very good if you're doing signal processing, but if you're not doing signal processing, it's no significant advantage for you. We'll talk about the differences there. People think the M4 is the latest, so therefore it must be the greatest and fastest. Not necessarily true. Now, it depends. We at NXP have an M3 running at 150 megahertz and an M4 at 180. So just by the nature of the fact that we ran one faster, it'll be more efficient. But in terms of the efficiency of the core itself, they're the same, unless you're doing DSP. So the LPC4300 actually has 2 cores. And I'll go in a little bit later of why we think that's a good idea, particularly for signal processing. But if you look at the bandwidth or the performance then, is you can add the performance of the M4 and the M0 together to get even greater performance. Okay, this drystone, let's look at CoreMark. CoreMark is another way that people measure processors to some extent, as it says at the top here. I pulled that off the ARM website. It's an improvement over drystone because the knock on drystone is it's perceived to be too tied into the compiler. So in this case, I picked some numbers. If you go to the coremark.org website, people will post their scores there. And we see on the very left side is an 1100 and M0 that is running at 48 megahertz, and the score was 50-ish, 50 point something. And these are already posted on the website. If you look at the 1768, which is an M3 running at 100 megahertz, you see I think it was 175 in that range. Now, the M4 runs at 180 megahertz. And so it's almost, I think, 380-ish on the performance. And this is running out of internal SRAM. The M0 at 180 megahertz, as you see, is almost the same efficiency as the M3 running at 100 megahertz. Now, if I wanted to, I guess I combine those scores, and then we're a CoreMark score of almost 600, I guess, if you're looking at the two. I believe they're all Kyle MDK. The two on the left, I'd have to check the website. But the ones on the right were definitely done on the Kyle. In this case, the code has been run from SRAM, yeah. What I haven't talked about is there are 2 versions of the 4300 and the 1800 parts. The first one is flashless with a large SRAM, and the second one is flash. So the flashless is coming out now. The flash is a quarter later. So we don't have the flash results posted. We have not published them yet. We will when we get to there. Which brings up a good question. So the question was, well, have you published results running from flash? So what CoreMark tends to be used for, let me take a step back. If everybody with an M3 or an M4 core runs CoreMark from internal memory on an M3 or an M4, it should be the same amount, 0 wait state. The score should be identical because it's really a measure of the core performance. It has nothing to do with the peripherals or the I/O. Assuming you have 0 wait state internal SRAM, the score should be identical. And what you tend to see is CoreMark per megahertz. And typically, you'll see 2.1 range for the high performance M3s and M4s. Then, of course, this is CoreMark measured times megahertz. So again, it's a performance of the clock speed. So the interesting question is, if it's all the same, what good is the value? Well, people have started to use CoreMark to measure the flash performance. Internal flash has wait states. There's no way around it. It's just not as fast as internal SRAM. NXP has patents around flash acceleration, how we pull data from the flash to basically act almost like a little mini cache. It's not a cache, but it acts that way. So you get more cache hits, and you don't suffer the penalty of slow memory. And so we get very good performance. Our competitors have more or less kind of caught up to that, to the point where we're all about the same in terms of CoreMark per megahertz. As you see, if you go to the website, you can see a lot of 2.17, 2.14 scores. So in other words, you're approaching the efficiency of an SRAM, and that's as best as you can get. So once you get to the flash to the point where it's almost identical to SRAM, you're bragging about 0.01 percentage points at that point. We'll have our scores. I'm sure we'll post them when we come out with the flash. So and I'm sure it'll be right in that position there. Okay, so let me give you an overview of what is in the 4300 family, which is the M4 M0 dual core. Again, two versions. It was designed in parallel with an M3. So we have this 1800 M3 and this 4300 M4 M0 dual core that are virtually identical from an IP point of view, with the exception of we have one that has the M4 and M0, and we added a little more SRAM because of the dual core into the M4 version. So dual core, both running at 180 megahertz. A typical M0 runs at 50 megahertz or below, so we've cranked the speed up on that, up to 180 megahertz. We have some new peripherals to talk about. We have a large amount of SRAM, up to 1 meg of flash. And then I've kind of done disservice, but a whole bunch of peripherals in terms of you can have Ethernet or LCD. We have an LCD controller for graphic LCD, not a segment LCD. Smart card interface, your normal suspects with UARTs and I2C and I2S. And I have another slide I want to talk about how do we differentiate. Well, everybody has I2C, everybody has UARTs, everybody has I2S, everybody has more or less up to 1 meg of flash now as they go into a different process geometry. It's worth mentioning process geometry, 140 nanometer, gives you the ability to go to about 512K of flash at a certain speed. As you shrink the geometry, you can have more flash. So now we're up to 1 meg as most of our competition. But we have some unique peripherals that we think are unique. And the challenge, of course, is how to explain them in a way that you say, oh, wow, that's a great capability. You don't know you need them until you need them. When we've done training, people are like, oh, I don't really want that. And they get the training on and go, oh, well, that's great. I really like that feature. So we'll talk through what some of those are, but those are the other two sessions that come later today. A block diagram view. Here you see the dual core. The neon green color, if you will, that's ARM IP. So that's what we license from ARM. That's going to be the same no matter whoever competitor it happens to be. Although some of those, like the memory protection unit and the floating point unit, are optional, meaning the licensee may or may not have included them. High performance M4s almost always have the floating point unit, but it's worth checking if that's of interest to you, because not every M4 from the competition has the floating point unit. Onboard ROM, some of the serial GPIO state configurable timer, or we call configurable peripherals. I'll talk about them. Anybody interested in USB here? Okay. So one of the things that we've added to this, so we have the capability for 2 high-speed USB hosts on most of the parts, actually, or some of the parts. We actually have a high-speed PHY built in. So you actually have not just high speed, but you have the high-speed PHY built onto the chip, which is a nice feature. And one of the reasons that is, of all these peripherals, the thing that excites a lot of people. It's also on the 1800, so we tend to see a lot of people looking at USB, audio streaming, high speed, on both the M3 1800 and the 4300. It's worth mentioning the 1800 and the 4300, as I said, were designed in parallel, so virtually identical. But I wanted to, going back to the advertised topic for this session, which is how do I make that decision? So when I tell people, or when I talk to customers, they might say, oh, I'm interested in the M4. I say, are you interested in signal processing? Yes, obviously the M4 would be a good choice. If they say no, I say, okay, well, are you interested in dual core in our case? And if they say no, I'll say, okay, well, how about the floating point unit, which is only offered on the M4? And if the answer to that is no, then quite honestly, you might be very happy with the 1800, because as you see, it has all those things we talked about. It has the high-speed USB, it has the PHY. It actually doesn't have the serial GPIO. It has slightly less memory. Other than that, pin-compatible choices for you, which makes it nice from a platform point of view. You can start with one, and if you need more performance, drop the other one in. Do you need signal processing? Do you need a floating point unit? Does dual core help you? And if not, 1800 might be a perfect choice for you. As we saw, the M3 and the M4, from an efficiency point of view, are identical if you're not doing signal processing. Okay, from a part number, and somebody was asking me about the different parts, we basically have 4 members of the family, or 4 groups. The flash list is on top, that comes out first, and then the flash is on the bottom. So you can see the 1 meg flash. So let's looking at the top, you see easily the 4 sections. The 4350 is what I call the kitchen sink part. It has all the features, the graphic LCD, Ethernet, 2 USBs, and all the other things that we've talked about. The 4330 takes off the LCD. So if you don't need an LCD controller, 4330s has your Ethernet, has 2 USBs, 2 CAN, all the other peripherals, I2C, I2S, etc. The 4320 has only 1 USB, and it's the USB with a high-speed PHY. So if you said, look, I just want 1 USB, I don't want to pay for the Ethernet and the LCD, I just want that, 4320 is the way to go. And if you say, look, I like all the other features, but I don't need Ethernet, maybe I just want to use the CAN, then 4310 has no USB, Ethernet, or LCD. It's the lowest cost part, but it still has all the other features that we've talked about. Obviously, one of the key reasons that the M4 was designed was for signal processing capabilities. So if we look at the block diagram, it looks very much like the M3, but now you have the floating point unit, and you have these extra instructions that have been added for SIMD and for single cycle multiply accumulate. And in fact, here's what those instructions look like, and you see the clock cycles. On an M3, that would take you 3 to 7 cycles to do a multiply accumulate, and that is tied to whether it's full 32 bits or whether it's really only 16 bits in terms of cycle time. The floating point unit has been added, and the floating point unit gives you a lot of benefits if you need the dynamic range. Doing floating point math on a fixed point processor is a bit cumbersome and takes a lot of time. So you can significantly improve cycle counts, as you see here, to do something equivalent on a fixed point processor to the floating point. Significant savings there. So I have another slide on efficiencies on that one. So SIMD, single instruction, multiple data. The floating point unit can be used by the C compiler, but SIMD is a little less friendly with C compilers. So we tend to see the benefits of SIMD as people who are writing optimized libraries, or if you wanted to do things that, maybe a stereo channel where you take 1 instruction and execute it on 2 sets of data. Anyway, the instructions are built into the core, and one of the things added from M3 to M4. Okay, for those of you who are interested, or at least a quick understanding, a very broad brush on DSP. DSP, the processors have been optimized traditionally to do FIR filters, IIR filters, and FFTs. And in fact, an FFT used to be the standard benchmark to compare different DSPs, or how fast you could do a single cycle multiply accumulate for the FIR filter. What these all have in common, as you can see, is multiply of a coefficient and a data value, a summation or an accumulation of the data to the output. The difference between the FIR and the IIR is the FIR, although it's hard to tell here, the configuration, typically you might have a large tap filter and you do 1 multiply accumulate over and over and over again. And typically DSPs have instructions or features to do things like 0 overhead looping. And so basically you don't have to reset the loop up every time. And they also have features to allow you to change your pointers and more parallelism, so you can actually fetch your data and opcode. The M4 doesn't have that. The M4 does have the single cycle multiply accumulate. It's going to be very good at the IIR and the DFT, and the FFT, sorry, which is the implementation of the DFT. And the FIR is going to be good, but if you only want fast FIR performance, well, that's what DSPs were built for. So we'll talk about the trade-offs there. ARM has gone out and created and licensed and created a whole set of libraries. So all of these features are done in libraries for you by ARM. So if you go to the ARM website, you get all of these features. You can see the cosines, filters, et cetera. So all of this has been optimized for you already. You just can go in, and it's a free library. It's built into their SimSys 2.0, so you can download that, and you already have all your signal processing capabilities. So quickly, let's compare. As I mentioned, the M3 can do signal processing. the M4 can do it better. So you might still not need an M4 if you're doing signal processing, basic signal processing. But let's look at a comparison of the differences. So the M3, as you see in the red here, sorry, in the blue, smaller is better in terms of the number of clock cycles to do instruction. And you can see for your traditional FIR, IAR, FFTs that the M4 is much better. That single cycle multiply versus the 3 to 7 of the M3 does make a difference. 16-bit functions, 32-bit functions, again, quite a bit of difference with that single cycle multiply. So that's comparing M3 to M4. So we said, okay, how does it compare to a traditional DSP or a traditional digital signal controller? So we went out and do some benchmarks on that. So as we took a look, was actually extremely pleasantly surprised at the results. If we look at the FIR and the IR and the FFT, we said, well, how do we make this a fair comparison, first of all? So we went out to a DSP processor, to their website, and got an equivalent library, so an optimized library from them. And then we optimized our own library and compared like for like, because we wanted to make sure that we weren't trying to be an expert on their code. So whatever was in their library. So let's start on the bottom. As we see from an FFT, we actually see for the very bottom, a 1024 FFT, we see that the cycle count of the 4300 is better, smaller is better. So we actually outperform a 16-bit DSP, which is the Blackfen, and a 32-bit digital signal controller, which is the C2000 core. So the M4 is very good. It's a 32-bit processor, so that gives us some advantages compared to a 16-bit DSP, a traditional 16-bit DSP. Very good at doing the FFT. IIR, we got very similar results. You can actually see we're very similar. We're actually better than the Blackfen. I don't know what happened with the C2000. We looked at this, and it seems like the library function that was available for the C2000 just wasn't that good. We're doing a like-for-like comparison. They could have optimized it a little bit better. I honestly think if they had a better optimized library, they'd be a little bit closer to the results. Now for the FIR, for a 32-tap filter, we were close, but the Blackfen with the dedicated zero overhead looping and some of the other features started to have a little bit of an advantage. So again, if the FIR is the one thing you need to do, a traditional DSP will have an advantage. But if you look at an IIR or an FFT, it starts to get very interesting with the M4. And now this is a fair playing ground where we're running from internal memory and we're doing algorithms. We're not talking about flash, which microcontrollers typically are very good at. We haven't factored in our dual core and the M0 capability. We haven't factored in any of the other features that we have in our microcontrollers. Now what's interesting is if you think of MP3 decode, MP3 decode is traditionally seen as a DSP algorithm that you would do in a DSP. There's a third party that coded this up, and these are ARM numbers actually. They coded it up on an M4 and got it below 10 MIPS. A discrete DSP, so there's your Blackfens, your TI parts, tend to be in that space. The M4 was more efficient in an algorithm, and the reason is it wasn't just multiply accumulate. There was some bit packing and unpacking that had to be done, and as it turns out, the microcontroller part of the M4 was better at that. So even at a system level, when you're looking at not just doing DSP, but something that's DSP-like or an MP3 decode, as it turns out, the M4 has an advantage because it's good at DSP and it's good at microcontroller. Which again, isn't to say it's not going to replace every DSP that's out there. It depends on your system and depends what you're doing. But it's something that you should definitely look at. If you have more of an ASIC specialized DSP, you can get even more efficient, but that's a dedicated processor for audio. I mentioned I'd come back to the floating point. If you're familiar with Mandelbrot, very complex equation, square root of a imaginary number. If you run this in fixed point, it takes 711 seconds on the M4. If you turn on the floating point unit, it takes 3 or 5 seconds, depending on whether you have that Mac feature turned on. So significant savings. Now, in fairness, I don't know how often you're going to do a square root of an imaginary number, but if you need the complex floating point operation, you have that built in as part of the 4300 M4. Okay, so we had some questions on dual core. We'll come back to that now. So why did we put dual core in? All right, M4 is good at DSP and microcontroller. Why do you need another microcontroller. Why can't the M4 do everything? And the answer is it can. M4 by itself is a great part. And in fact, we'll see in our portfolio, we'll have versions of the part with the M4. So the M3, the M4, or the dual core, what we really want to do is give you choices. And we started what we think is the hardest thing first, which is the dual core, and we will certainly have single M4 capabilities as we move forward. But let's think about signal processing in DSP. If you've ever programmed real-time DSP, you can't be away too long from waiting for that next interrupt to come in because you've got to service it, you've got to do your filter, et cetera. If you're off servicing a USB routine or Ethernet routine, you're getting a lot of interrupts, your system becomes much more complicated. So we said, well, we've got the capability. We have the M0 in our portfolio. We have the M4. The M0 is a very small gate count compared to all the other things we have in the chip, very small gate count. And we have the knowledge to know where to put it and make it run fast. So we said, let's put it on there. And what that gives us is the ability to have the M4 be completely focused on signal processing or whatever task you might be looking to do, and have your M0 handle all the I/O capabilities. So now you have the M0 ROM drivers, as we talked about. The M0 can be handling that, and you get the M0 chugging away at USB or Ethernet, so you don't have to be bothered with that as you're programming the M4. So it gives you more capability, and it should actually simplify your design as you partition things, as you start to add complex peripherals like USB and Ethernet. What this shows here, though, is the difference between symmetrical dual core and asymmetrical dual core. Symmetrical dual core is what you think of when you have that quad Pentium, 4 things that are dividing up a complex task equally, and they're all running and dividing up one task. That's not what our dual core is. We actually have a sort of a big little approach, and the little mean the M0 can handle those I/O capabilities or things that require less power, while the M4 is either asleep or chugging away at something more important. So an asymmetrical dual core has 2 cores that are of different sizes and or different capabilities. Traditionally, you think of an asymmetrical dual core as an OMAP. So TI has the DSP microcontroller built together. The challenge with that is you have 2 separate tool chains, separate programming. In this case, we already saw before, the M0 and the M4 share the same instruction set, so they both can run the code that's in ROM, either one, you can pick, and they also share the same tool chain. Actually, it's one JTAG that will connect to both cores and allow you to debug. So that is the difference here between, so it's not that you would take a task and divide it between the 2 cores, is that you would partition different tasks, USB over here, DSP over here, between the cores up front. And I've already actually talked through that slide, but basically frees up the M4 core to do signal processing or high performance operations, and it makes it easy by separating your real time from your control code. Any questions on, I have a couple more slides on dual core. One question that comes up is, okay, well, which one has access to memory and which one has access to this peripheral or that peripheral? One of the things we did is we put them both on our bus matrix, so both have complete access to memory, anywhere in memory, and complete access to any peripheral. So that's a tremendous amount of flexibility. That means you as a developer get to, it's like picking teams. Okay, the M0 gets this one and the M4 gets this one, and you really want to partition it. If you do that, you'll have the least amount of contention, and they can almost independent as if separate processors with separate peripherals. A way to look at it is inside the core, we have a bus matrix, and the bus matrix has the ability to avoid contention. The Cortex-M4, and we also, we're saying, we divided our memory into different banks of memory. So our SRAM has 4 different banks of memory here. So you can have the M0 running from one bank of memory and the M4 running from a different bank of memory, 0 contention. We have, if you have flash, we actually have 2 banks of flash. And I haven't spent time talking about flash, but we have dual bank flash. Are you familiar with that? You can actually program one while you're executing from the other. Or you can have the M0 tied to one and the M4 tied to the other. Or you can have the M4 tied to the flash and the M0 only running out of SRAM. Lots of choices to give you the maximum flexibility as you're developing your system. Okay, just some applications of, all right, where would I use the 4300? Where would I use the 1800? Certainly from an 1800 point of view, it's very similar but without the signal processing. Still very good in the USB and audio space. Very good in the industrial space. And with the M4, it opens up some more capabilities because of this signal processing. But maybe a better way to look at it is just looking at it from some block diagrams. But first, I want to reiterate some of the unique peripherals that we have. And I'm doing pretty good on time, so 4 unique things that nobody else has that we have put in this processor. 3 are peripherals, and 1 is the dual core that we've already talked about. And I explained why we did the dual core. So serial GPIO is a way of, how many people are familiar with the term bit banging? Yeah, okay, so if you had to bit bang, if you had to interface to some non-standard interface, how would you do it? You'd set a timer, you'd have to get your processor to interrupt, change a level. Basically, you're using your processor to create a waveform. Well, the serial GPIO gives you some shift registers attached to dedicated GPIO lines that allows you to program it in a sense or configure it to basically be that interface. So you can avoid bit banging by actually using the serial GPIO and configuring it to be that interface for you. So you can interface to any non-standard interface. We give you up to 16 lines, so it could be 1 bit or a 5-bit interface or an 8-bit interface, 16-bit interface if you choose to. It can also mimic standard interfaces. So as you go through the selection guide and go, oh, gee, too bad you didn't have another I2S. Well, this could be the I2S for you. This could be the I2C, the UART, whatever you want it to be from a serial interface point of view. Still digital logic. Or you can tri-state, which is important for I2C. If you go to the booth, you'll see a demo where we're doing audio. We're using the serial GPIO to be interfacing to audio codecs, simulating I2S and 5.1 audio. The state configurable timer, and again, that's both of these are covered in the session, the second session coming up, is a way of doing timers and PWMs in basically a state machine system. So if you think about a PWM, it gives you 1 waveform. We actually give you up to 32 states, and each state can be triggered by a different interrupt or by a timer. So in fact, you can create your own any complex set of waveforms or interface for timers and PWMs using the state configurable timer. Okay, some demos. I think I more or less talked through these. This is a demo we have in the show floor now. Basically, USB coming through, controlled by the M0 using the ROM drivers, passing data through the interprocessor communication, which is just a handshake, to the M4 to do audio processing. And in this case, it's a biquad IIR filter, or it could be anything you want it to be. And then passing back out through serial GPIO to 5.1, well, actually in this case it's several codecs, but out to multi-channel audio. So a great way to actually use the dual core, because now you completely have the full bandwidth of the M4 to do signal processing. In the industrial side, you can actually have the M0 handling the CAN interface and getting commands in the industrial space. And then the M4 can be using a dedicated motor control PWM and our state configurable timer to interface to different motor controls. You can have dual motor control on the part, for example. High-speed USB through a thumb drive, so mass storage class, high-speed USB using the M0. This is an M3 example. But the high-speed USB, it could also be in the M4, using the external memory controller and going out to the LCD controller. And this is basically the example I was mentioning before, which is you can put a large amount of images outside in your quad SPI flash. It'll look like a memory mapped interface, and you can have the LCD controller directly pulling out of SPIFFE or a SPI flash interface and displaying it without the cores having to be involved. So you use DMA there to pull it right out of memory. It's as if it was internal memory for you, but big chunk of external quad SPI flash. So just some examples for you of different configurations. Okay, so just a couple things to mention. A little known feature is you may have a 100-pin part, but we have a really extensive pin muxing, which means any one pin can be almost up to 8 different things. So usually on a 100-pin part, you have to choose a certain configuration. We make it really easy for you to, well, let's say I want these peripherals. You can set up your matrix, your pin muxing, to determine which peripherals and use a smaller part. So basically, the pin muxing allows you to use a smaller part and get the things that you want in that peripheral. LPCware.com is a NXP sponsored site that we want it to be more of an engineer to engineer where you can go get code, get examples. You can upload code. So it's a community site or an engineer to engineer site, but that is a good place to go if you're interested in software or examples or schematics. LPC Zone, Twitter, YouTube, more from a what's coming type of thing. Yahoo Groups is a group that a lot of people use to communicate about LPC, so any NXP microcontrollers. If you're interested, we also have a bunch of videos on YouTube. Look for LPC Zone. So if you want a 2-minute explanation of what is the 4300 or what is the difference between the 1800 and the 4300, you can go here. And lastly, if we go back to the abstract, I promised a sort of view of what was coming in terms of a roadmap, so I wanted to be sure to mention this. So our 4300 family, our flashless parts are coming out now. Our flash parts will be next quarter. And in terms of a few more peripherals that are coming, we see the 43S part. So I had a question about the AES. That is the part that has AES encryption. So it'll be 43S for if you want the encryption and the decryption. The 43A part is a part that will have a very fast ADC on it, even faster than the ones that are already on the chip. And we'll have more about that in the coming month or two. And I'll mention one more in the very low end there, the 4000 family. So all the parts in the above are pin compatible with the 1800, but we had a very successful 1700 family as well in the M3. So we actually have an M4 that will be pin compatible in that space to give people who are already using those parts a roadmap. All right, thank you everyone.